In traditional large language models, or LLMs, built using the transformer architecture, most of the heavy lifting is done using 16-bit precision. This means the model works with numbers that have a lot of details, which requires more computing power. The biggest cost comes from doing things like matrix addition and multiplication, where the model is crunching through large amounts of data. Another challenge is that these models need to load information called weights from memory, like DRAM, into faster memory on the chip, like SRAM, when it's running. This transfer takes time and energy, adding to the cost. One solution people often use to make things cheaper and faster is called post-training quantization. This is where you reduce the precision of the numbers from 16 bits down to just 4 bits. This helps the model run more efficiently during inference, but it comes at the cost of losing some precision in calculations. On top of that, some people try to make the model faster by adding more SRAM to improve speed. However, this is expensive because SRAM costs more than DRAM. So, while there are ways to make these models run faster and use less power, they come with trade-offs that need to be carefully considered. Imagine you're trying to build a smart computer model like a language generator, but you want it to run faster and use less energy. Normally, these models work with big numbers that need a lot of power to calculate. BitNet 1.58 is a clever solution to make this faster and more efficient. So, how does it work? Normally, in these models, numbers can be really large or small, but BitNet uses only 3 simple values for these numbers: -1, 0, and 1. This makes the model much lighter and faster. The trick is in how it decides to pick these values. It first looks at how big the numbers are on average, and then adjusts them to either -1, 0, or 1. This process is called quantization. Now, the architecture behind BitNet is a bit like a building plan for a model. The regular model would use complex operations like floating point multiplication, which takes up a lot of time and energy. But BitNet 1.58 replaces these with much simpler operations, like adding integers instead of multiplying them. This makes it way more efficient. Even though it's much simpler and faster, BitNet 1.58 still performs as well as traditional models, matching them in accuracy. It can handle tasks like understanding and generating text just as well, but it does so with less memory, faster speeds, and lower energy use. In short, BitNet 1.58 is like a smart shortcut for building powerful models that still do their job perfectly, but without wasting resources. If you're interested in exploring some 1-bit language models, you can find them on Hugging Face. I've shared the links in the video description below, so feel free to check them out and dive deeper into how these models work.